Welcome to the course Advanced Reaction Engineering. So, today we will discuss about the basics of non-ideal flow that already we have discussed in our previous class also. So, this is continuations of that. So, today we will discuss about the residence time distribution functions or RTD in ideal reactors. So, that reactors may be batch reactor, plug flow reactors or CSTR reactors. Okay. So, RTD in batch and plug flow reactor first we will discuss, and then single CSTR or ideal CSTR reactors residence time distribution functions we will discuss, and then mean residence time distribution functions for a CSTR, variance of residence times in a perfectly mixed tank or CSTR reactors we will discuss. Okay. So, now first we will start the RTD for a batch and plug flow reactors. So, once we have a batch reactor, this is a batch reactors and this is a perfectly plug flow reactor, this is PFR reactors and this is batch reactors. So, in the batch reactors we usually conduct when experiments. So, we just take the reactors and put the reactant mixtures inside of the reactors and we spend for 30 minutes 20 minutes. Once the reaction is over, then we take out all the reacting mixtures or the product mixtures. So, here in this batch reactor there is no inlet, no outlet. So, this part is no and this no means inlet input output is no, there is no. So, therefore, here we can say that this batch reactor is an ideal reactor. So, here all the molecules whatever we charged inside of the reactor spent equal times for that total experiments. Okay. In case of the perfectly plug flow reactors also, if we say that this is the reactant molecules once it is entered inside of the reactor, after that it gradually moves this way. Okay. So, the movements of that reactant molecules spending equal time. So, in these two cases we can say the reactors are ideal. So, in this case when the reactor is ideal reactor, so here you can see that the ET curves. ET means residence time distribution functions for this type of reactors, usually a vertical lines is coming. So, that is called spike. Okay. Spike, this is called spike. This type of reactors when batch reactors or plug flow reactors, if we conduct the treasure test in this type of reactors, these are since these are the reactors are perfect ideal reactors. So, then if we want to find out the ET, means first we have to find out the C curves for this particular reactors. Once we know that concentration at a particular time, and then we convert that into residence time distribution functions or ET. So, E curves that is means at this particular time, that is the tau, it would be spike. Okay. So, with infinite height. Okay. So, therefore, this type of means when ideal reactor is there, this is nature of ideal natures of E curves. In most of the cases E curves usually comes like this, but when it is ideals, so it would be like this, sometimes it is coming like this. Okay. So, it may be like this. So, it indicates ideal to non-ideal natures of that, means from the E curves we can say whether the reactor is perfectly ideals or not. Okay. So, now this type of spike or E curves, mathematically this spike is represented by direct delta functions and it is expressed in terms of Et equals to delta T minus tau. Okay. So, for batch reactors and PFR reactors, plug flow reactors, ideal batch reactor, ideal plug flow reactors, residence time distribution functions Et is delta T minus tau. So, what is direct delta functions? So, delta function has the property delta x equals to 0 when x not equals to 0 and delta x equals to infinite when x equals to 0. Okay. So, this is the property of a direct delta functions, and delta functions we can express minus infinite to infinite delta x dx equals to 1. If it is like this integrations, so then it would be final result would be 1. Okay. If it is like this, so then this is the delta functions, this is the function gx. So, if we integrate gx and multiply it with the dx and integrate that with respect to the dx, that result should be g tau. This tau would be here Okay. So, this way we can get G tau, that is the results. Okay. So, this is the delta functions how we can mathematically express or its property that we have discussed. So, now means mean times, mean residence times or Tm, that usually express mathematically this way, these expressions. So, here we said that this for ideal reactors ET residence time distribution function expressed this way. So, this ET we can substitute here. Okay. So, then Tm equals to T delta T minus tau dt. So, the results of this would be tau. So, Tm equals to tau. Okay, mean residence time distributions or mean residence times for this ideal reactors it would be tau. Similarly, for variance also. So, variance we can express in terms of sigma square 0 to infinite T minus tau whole square E t dt. This is the variance definitions. Okay. So, here also for ideal reactors if we substitute this, then this would be like this. Okay, sigma square equals to T minus tau whole square delta T minus tau into dt, and the results would be, if we integrate this it would be 0. So, here's T minus tau, here it would be the tau minus tau square equals to 0. So, sigma square equals to 0 for ideal reactors. So, whenever a ideal batch or plug flow reactors we have, the things we can say that for ideal batch or plug flow reactor mean time equals to tau, sigma that is the variance equals to 0 that we have discussed, and Et equals to infinites, okay, infinite heights, and Ft equals to 1. So, Ft equals to 1 for perfectly or ideal reactors. Here C output that would be equals to 0. So, then C 0 by C 0 equals to 1 we can say that way. So, Ft also would be 1 for a ideal systems, ideal reactors. Okay. So, here's Ft also this way also you can express. So, Ft equals to 0 to T Et dt. So, here Et equals to delta T minus tau. So, here it is substituting here and then it is 1 you can say. Okay. So, for there is no variance and Ft equals to 1 for ideal reactor. So, here's E functions or E curves is like that, Et for ideals and actuals is like this, and Ft curves also is like this, that already you have discussed. So, no need to discuss more. So, now we go for a single CSTR we have. So, means batch reactors and PFRs, ideal plug flow reactors and ideal batch reactors we have discussed. Now, we are going to discuss for a CSTR reactors. Okay, third reactor, that is the CSTR reactors, and this is called CSTR reactors. So, here in this type of reactors mostly means non-ideal natures usually we found. So, this is effluent stream concentration here, this is feed concentration, that is feed entering here, and tracer or the effluent after reacting that we are collecting from here and we are analyzing. Okay. So, in this type of reactors if we do the material balance on an inert tracers that has been injected as a pulse, here we are injecting pulse tracers at a time t equals to 0 and for t greater than equals to 0. So, initially just pulse injections of tracers we have injected here, pulse tracer injections. So, here's output from the outlet of the reactors we will get the tracers and the time t greater than 0. Okay. So, input equals to 0, since there we have not, once we sort of tracers that may be 10 milliliter, 5 milliliters tracer that have been injected here, after that only feed is passing, so there is no tracers. So, this input concentration of the tracer is 0, from the output or outlet concentrations if V equals to volumetric flow rate is this and concentration at this particular here is C. So, this is the concentrations of the tracer that we can find out, and if there is accumulations inside of the reactor that we can write V into dC by dt, this way, this is the material balance. Okay. So, here V is the volumetric flow rate and V is the volume of the reactors. Okay. So, now if we take these equations and rearrange these equations. Okay. So, here tau equals to V by V naught. Okay. So, here is V, here is V naught. So, therefore, tau is coming and rearranging these equations, and after rearranging we can get this, and now we integrate these differential equations 0 to t time or tau dt. Here these equations dc by c minus is also coming. Okay. So, if we integrate this with respect to this, then we can get the concentrations. Okay. So, it is wrong, means 1 by tau would be there. Okay. So, here after integrating this we can get C t equals to C naught into e to the power minus t by tau. Okay. The outlet concentrations of the tracer that is coming out from the reactors here C t at different times equals to, if you know, initial concentration of the tracer that has been injected at different times, tau is that fixed volume by volumetric flow rates. So, that is the constant. Here t is the variable and C t is the variable. So, with t C t, okay. Rest tau is known, C 0 is known. Okay. So, these are the constant value. So, then we can concentration of the effluent concentrations we can find out. Okay. So, now for this is we have derived from the material balance. So, now E t we can express for an ideal CSTR is equals to this C t by 0 to infinite C t dt. So, E t this way you can write. So, now this C t you can substituting here and denominator both the places. So, then the equation should be like this, and after integrations we can get this. So, here after E t curves we can write this way, E t equals to e to the power minus t by tau, that is for single ideal CSTRs, that would be this. Okay. Similarly, for cumulative distribution functions or f t we can write f t equals to 1 minus e to the power minus t by tau. How that is coming, that we will discuss. Okay. So, from here easily we can find out. So, how that is coming, so that we will discuss. So, now if we have these equations, okay, this is E t for CSTR reactors, E t for batch reactors or plug flow reactors we can express this way, and for CSTR reactors E t we can write this way. Okay. So, this is the basic difference. So, you should know about it. So, now if we have this table, so then we can theoretically we can calculate E curves, E t versus t we can plot, F t versus t we can plot. These are the things known. So, then means E t curves would be like this, okay, and F t curves would be like this. Okay. So, from these equations and these equations, so easily we can E curves and F t curves easily draw for the ideal CSTR reactors. Okay. So, now we can expressing the same things in dimensionless forms. Okay. So, theta equals to t by tau, E theta equals to tau into E t, or E theta equals e to the minus theta. Okay. So, E t F t we can write express in terms of dimensionless forms. Okay. Dimensionless forms E theta F theta. So, similarly, here E t against t we have developed, F t against t we have developed. Similarly, in the dimensionless forms also we can develop, this is E theta curves, this is F theta curves. Okay. So, dimensionless forms, that way also we can express, and F theta I said how to get it. So, here F theta equals to 0 to theta E theta d theta, that would be this. Okay. So, earlier this how F t we got. So, this way we can write. Okay. Now, we are coming to the mean time, mean residence times for a CSTR. So, mean residence time distribution function or express the equation this way, T m equals to 0 to infinite T E t dt. Okay. So, here E t equals to for a CSTR reactor equals to e to the minus t by tau by tau. So, this we are substituting here, and then we are doing the integrations. Okay. Here one t would be there, I think. So, then after integrations T m equals to tau we can get. Okay. So, Tm equals to T from here we can get. Similarly, for variance of the residence times for a mixed perfectly mixed reactor sigma square, the definitions is this. Here Et we can substitute it here, this Et we can substitute here, and after substituting if we do integrations, so then sigma square equals to tau square that we get. Okay. So, sigma Tm equals to tau and sigma square equals to tau square. Okay. So, this way you can write, or sigma equals to tau. So, for a perfectly mixed CSTR reactor, mean time equals to tau and sigma equals to tau, and Ft equals to this, Et equals to this. This way for a CSTR reactors we can summarize that residence time distribution functions Et for a CSTR reactor is e to the power minus T by tau by tau. This is residence time distribution functions, and mean time equals to space time, and variance sigma equals to tau, and Ft equals to 1 minus e to the power minus T by tau. Okay. So, here's batch reactors and plug flow reactors, Tm equals to tau, it is if it is ideal, sigma equals to 0, Et equals to infinite, Ft equals to 1. This is for batch reactor and CSTR reactors, Ft equals to 1, Et equals to infinite, sigma equals to 0, Tm equals to tau, and for CSTR reactors Tm equals to tau, that is the common in both the cases, and here sigma equals to tau, there sigma was 0 and here sigma equals to tau, here Et equals to e to the power minus T by tau, and in that case of batch reactors or perfectly plug flow reactors Et was infinite. Okay. Et was infinite and Ft was 1 in case that, and in this case Et equals to 1 minus e to the power minus T by tau. These are the means summary of these two different means ideal reactors, how to express in means once we know the direct delta functions. So, we can put that and to find out mean times variance for a ideal batch and CSTR reactors, and for CSTR reactors perfectly mixed CSTR reactors, for that case we can find out the residence time distribution functions and Et in terms of T and tau, and then we can find out mean time, sigma and Ft. Okay. So, I think it is clear. So, today is up to this. Thank you.